so I just wonder whether you can hear me or not. Please tell me. Okay, nice. Okay, just a moment. Okay. Саша, будем ждать тогда, будем ждать тогда микрофона или нет, как вы скажете? В принципе, я говорю сейчас через свой микрофон, вот, наушники.
Чтобы на YouTube записалось лучше.
Да, те, кто смотрит через YouTube. Окей, тогда мы сделаем так, как в прошлый раз. Как много разных микрофонов. Окей. Please check. Просто проверьте, как там все это работает, потому что я немножечко запутался в этой. Нужно, чтобы меня слышал YouTube. Zoom.
Кстати, здесь знаешь, как работает, как я в прошлый раз делал у нас вот, без этого. Я могу еще приносить планшет вот этот вот, на котором можно писать.
Но это немножечко. Это немножко противоречит доске и камере.
Если это транслировать на экран, камера будет снимать экран.
Понятно.
Но это, конечно, сложно, очень сложно.
Но это совсем усложняет жизнь. Так. Все работает, хорошо. Значит, единственное, что нужно решить, прежде чем начинать, буду ли я говорить по-английски или по-русски. В прошлый раз в YouTube было несколько недовольных людей, которые писали, что это такое. Почему это по-английски говорят?
Потому что мы транслируем в Китае. Вот Джунху тут уже и, наверное, скоро подтянется.
Да, второй. Хорошо. Okay, so I'll go on in English. Okay. So last time we spoke about the general quantization principle, and I introduced the so-called Moyle product. Let me briefly recall what it is and its properties. So suppose we have a vector space V, and we have some, say, bilinear format, okay, a tensor of indices, 0, 2 indices in V. So it is 0, 2, it is just an element of V tensor square, right? We also then we can introduce the product in the space of formal power series of smooth functions on V with coefficient with formal variable h bar, and this product will verify the following conditions. So first of all, it is associative. Second, it is H linear, or probably it should be put as the zero part of my condition. So zero part is this product is H linear, star product. When I say H linear, it means that whenever we have H bar times F and we star product it with G, we just have H bar times the star product of F and G. And of course it should be also additive in the sense that if we have the sum of F and G and we take its product with H, not H bar but just H, then we have F star H plus G star H. So these two conditions are very natural, so I'll just put them as zero condition here. So the first condition is associativity, that is to say F star G is equal to times H is equal to F star G star H. And then we also have the condition that the unit 1 in this space of smooth functions, is the unit in this product, this star product. And now the most important part of this condition, the most important after the associativity condition, is the following condition, that the first two terms of this star product are given by the standard formula. So actually the first term is just the usual product, commutative product of f and g, and then the first degree in H is the Poisson bracket of f and g with respect to pi. So when I say the Poisson bracket, I mean the following formula. If you have a function f smooth on v, and its derivation, its differential df is, well, at every point x in v is just an element of a dual space v star. So when you have two differentials, df and dg, you have two elements in the dual space, and then you can pair them, tensor them with, pair them with, couple them probably, better say, couple them with the element in the dual tensor product. Now, this is not skew symmetric, so the only thing we do, we skew symmetrize this. If pi is skew symmetric, then there is no need to do this, so probably I just introduce this additional condition, skew symmetricity of this element. It is not necessary, but it is nice to introduce it. Sometimes, in some texts, people also add the purely technical but important sometimes condition that the coefficients of this formal power series. So let us look here at the very first condition here, right? As you see, this H linearity and also distributive law means that for us to determine this product, it is enough to determine just the product of two elements f and g in C star of v, right? So C infinity of v. Because then we use this distributivity law and the H linearity condition to to extend this product to any pair of formal power series f and g, right? So when we look at this star product of f and g, and it will be a formal power series with respect to the variable h bar, and coefficients of this formal power series will be certain functions, smooth functions in v, on v, depending on f and g. So there is a very natural way to determine smooth functions when you have two given smooth functions, and this is by using bi-differential operators. So I usually introduce bi-differential operators, so it is done by definition, more or less. So these coefficients are bi-differential operators on f and g, in f and g. And the technical condition is that these operators are either symmetric, so b to k of f and g is equal to b to k or gf, that's symmetricity, or skew symmetric, b to k plus 1 of f g is equal to minus b to k plus 1 of f of gf. right? So this condition is more or less technical. Actually, this one is also technical, and in many cases, it is convenient to omit them. In many cases, in many situations. But in the case which we consider here, in the case of Moyle product, this condition is verified, and moreover, the products we are going to talk about today will also verify these conditions. So, well, at least the second one. As far as the fourth one is concerned, well, it depends. I think it is possible to make it so, but we shall see. Okay, so let me recall the formula for the Moyle product. The formula is as follows: F star G is equal to the product. M in this field usually stands for the product in the space of functions of the following formal by differential operator: exponent of h over 2, h bar over 2 of pi ij di tensor dj applied to f tensor g. So physical literature, it is they often write d I tensor dj. They use these two arrows to determine which element is acted on by which partial derivation, but I think we shall skip this notation for more or less. So if you just run across this notation, make sure that you recognize it, but we shall not use it. As you see, this formula is pretty simple, and actually it appeared from the study of some analytical approach to quantum mechanics. So it is completely justified. But as it is often in mathematics, when you have some justified formula, you ask if it is possible to introduce similar formulas in more general situations. One of the reasons why this question is totally well, valid in this case is that when you work in vector spaces with this kind of well, brackets, right? With this kind of brackets, they're called Poisson brackets. It is usually very hard to distinguish two brackets if you allow nonlinear transformations of coordinates. For instance, if you have, say, I don't know, something very simple like standard Poisson bracket, which I used last time, pi commutes with qj by delta ij, and then you pass to the variables f I equal to the exponent of pi. Say you introduce the condition that pi is positive, which is totally justified, totally normal, and qj, say, also is exponent, sorry, gj is exponent of qj, then the commutator of fi and gj will look like, I think it will look like delta ij, so please correct me if I am wrong, delta ij times fi gj. So this is nonlinear, this is quadratic, but of course it makes very little difference with what we had before. On the other hand, if we have a nonlinear, non-constant coefficients in this kind of tensor and try to introduce similar formula, and this formula will fail to be associative. The most important condition of all is the associativity condition, which is definitely the reason, as they say in French, raison d'être for all these signs. This condition fails at once if you use this simple formula in case of non-constant coefficients of bivector. So this kind of operator is often called bivector field. Right.
That V is finite-dimensional.
Yeah, Yeah, everything is finite dimensional. Yeah, sure. That was a question, I believe, right? But yeah, infinite dimensional case, I must confess that infinite dimensional case, as far as I can understand, as far as I know, is still not known. The quantization of infinite dimensional Poisson structures is not given, cannot be given by the known formulas. The known devices fail to work with this. People use some ad hoc constructions in every case. There is no universal infinite dimensional case construction. Okay, so this is the Moyle product, and I explained that our purpose now is to generalize this to the wider scope of bi-differential operators of this sort, by vector fields of this sort. So first of all, we need to set the to settle the set of examples we're going to consider. So that's why the first part of my talk today will be the most basic introduction to symplectic geometry and to Poisson geometry in some sense. And I hope that by the end of this talk I'll be able at least to give some first steps towards the field of quantization in that case. Okay, so first of all we need to settle the domain of our theory, and to this end I'll give the following definition. Suppose we have a smooth manifold M. I shall say that M has some symplectic structure, that a symplectic structure of M is given if we have chosen differential two-form omega on M, which verifies two conditions. First condition is very nice, and the invariant is that this form should be closed. The omega should be equal to 0. But this is not enough. And the second condition is, in my sense, less geometric, less invariant, but it's also very nice. It is that omega is non-degenerate. Non-degenerate. So what is non-degeneracy? Well, there are different ways to look at this. The most naive way is to say that locally, when we introduce coordinates in M, this two-form is represented by skew-symmetric n by n matrix, where n is a dimension of M, right? So if this matrix is non-degenerate, is invertible at all points of M, then we shall say that omega is non-degenerate. There is another more probably invariant way of looking at this, is to say that if you take the wedge product of omega with itself as many times as we can, actually we just take a dimension of M and divide it by 2, right? Then this should be a non-zero differential DMEM form. Nowhere zero, non-vanishing, not just non-zero, non-vanishing. Let's put it this way. Actually, it is more or less clear from what I said that the dimension of manifold which allows such structures should by all means be even. Actually, it is clear that whenever you have a skew-symmetric matrix of any dimension, then its determinant vanishes unless the dimension, the size of this matrix is even. This is a basic property of determinants. So we automatically fall into the case of even-dimensional manifolds. In this case, this ratio is a natural number, and this is a natural power here, and what we have is just a top degree form on M, right? So from now on, I'll say the dimension of M is 2n. Okay.
At every point.
So yeah, this is non-vanishing at every point, non-zero at every point. Yeah, sure. So of course there are lots of things you can speak about. You can do with such a form fixed on a manifold. For instance, as an exercise, I suggest that our audience try to prove that the even cohomology of any symplectic manifold, that is a manifold with symplectic form on it, of any compact symplectic manifold, should be non-zero. Even cohomology at every degree, at every even degree. So you have a compact symplectic manifold, then its even degree Dirac cohomology should be non-zero at every even dimension. That's a good exercise, and try to prove it. Also, yeah, it's standard exercise. Yeah, sure. Yeah, it's very nice and simple, but yeah. Also, what else we can do? Yeah, also it is nice to try to prove that these two conditions are equivalent. The equivalence of non-degeneracy of a matrix and the fact that its top degree wedge product with itself is non-zero at every point is also a good exercise, actually. I think both of them are worth doing. Okay, so from now on, I work with such structures of manifold, and I introduce a very important notion. Definition. Let f be a smooth function on a symplectic manifold M. So omega is symplectic form. Then there exists a vector field x sub f in vector fields on M, a smooth vector field, such that, actually unique vector field, such that x sub f, when you multiply it by omega, so when you take x sub f and apply omega to it, and take any other vector field omega, what you get is y, probably minus, yeah, I think it is y minus y applied to f. So it's up to sign, actually. A definition of this vector field xf, which is called Hamiltonian vector field. Hamiltonian vector field. So the definition of a Hamiltonian vector field is sometimes they change the sign here. Sometimes they do, sometimes they don't. So as far as I can remember, I'm used to this notation. It doesn't actually change very much, but I just set it like that. So the existence and uniqueness of such vector field is actually determined by the fact that omega is non-degenerate. That's why we need non-degeneracy. That's why we really need it. In coordinates, well, up to the sign again. I'm not sure about the sign, but let us check it. In coordinates, x sub f is equal to the raising of the indices. So this operation stands for the raising of the indices of the differential of f. So omega is a two form, so its inverse, omega minus 1, is a section of the exterior square of tangent bundle of M. Right? And locally, so that we denote by pi, just like in previous case. So locally, pi is equal to pi ij in local coordinates, right? So this operation here is just pi ij df dxj in local coordinates x1, x2, and so on, xn. The sum over j is assumed. So I believe even the sign is correct here. Please check it if I'm not. This formula is nice, and it is helpful when you need to do some explicit computations, but for theoretical purposes, it's a little bit, well, it's not redundant, but it's not necessary. Okay, let's go on. Now, the main property of Hamiltonian vector fields, which actually explains the interest in considering these vector fields, is that following statement is true proposition. For any two, so for any sorry, not for any two, for any function f, the Lie derivative of the symplectic form with respect to the Hamiltonian vector field of f vanishes. So let me sketch the proof here. The proof is pretty simple. I'm using some general knowledge from differential geometry, something like, actually I'm using the Cartan formulas from differential geometry. There is a different way to prove this, which you can find, for instance, in Arnold's book, a more geometric way to prove this, actually. But I prefer formal proof, which is totally fine, in my opinion. So, to this end, I do the following thing. When you have a vector field x, not necessarily, but doesn't matter what kind of field you consider, and you take the derivative of a differential form, any differential form, not in a necessarily symplectic or two-dimensional degree 2 differential form. So any differential form phi should do. So when you do this, when you take the derivative of phi with respect to x, you can decompose this, represent it as a sum of two operations. The first operation is the de Rham operator d applied to phi. This increases the degree of the form by 1, but then we take the convolution product of the form we obtain with respect to x. And then we can also do the opposite. We change the order of these two operators. So we first take this convolution, and then we take phi, and then we take the de Rham differential. I'll probably need parentheses here. Okay? So this is the Cartan formula. And also, I will need the Cartan formula for the de Rham differential in terms of these standard operations. I'm not even going to use the general formula for this de Rham operator in terms of Lie derivative and convolution and so on. I only do this for the degree 1 form. So for any degree 1 form, so this is in general, and this is for any 1 form. For any 1 form, phi, when we take differential of phi, it will be a 2 form, so we can compute its value at any two vector fields, and then we have the following formula. So first we take phi applied to y, and so this is a function, and then we take the vector field x and compute its value at this function. Then we change the order of the vector fields, and then finally we subtract one more thing, which is very natural here. It is the phi applied to the commutator of the vector field x and y. I think this is the correct. There is a problem with signs as usual in this case, but I believe this choice of signs is correct. So now we shall use these two formulas, and this will prove the proposition in just 2 lines. So actually, well, since omega is closed, the omega is 0, so we see that Lxf of omega, it is a 2-form again. So when we apply it to a vector field, to a pair of vector fields y and z, right, we shall have the following combination. So out of these 2 terms in this sum, only the second one will survive. So we shall have d iota x sub f applied to omega, and all this combination applied to y, z. Now, so let us denote this by phi. So now we use the second formula, and this will give us y applied to phi of z minus z applied to phi of y minus phi applied to the commutator of y and z. Now we recall what is phi of z. Phi of z is the what is phi of z? What is phi actually? Phi is the convolution of omega with yod x sub f. So when we apply, say, y here or z here, doesn't matter which, it means that, well, up to, again, sine, it will be just omega x sub f times z. So actually there can be 1/2 somewhere, but I think it is not necessary because it's skew symmetricity and everything. It's just this. Okay? But we can now extend this further because of the definition of the Hamiltonian vector field. So this is actually equal to z applied to f. So let us continue this formula now with the help of this observation. So what we have here is y applied to z applied to f minus z applied to y applied to f. Sorry, I think I forgot the sign. So minus and plus. Have to change the sign. That is important here. Otherwise, it will not cancel out. And finally, we have minus. Again, what is this? yz, the commutator of y and z, applied to f. And as you see, it's precisely the definition of the commutator here. So it cancels out, and we get 0. So as I promised, since this holds for all possible vector fields y and z, the Lie derivative of omega with respect to x sub f is equal to 0. This is a very important, although quite simple observation. And, well, while I erase in the blackboard, you can write yourself down a new exercise. Proof that Hamiltonian vector field preserve the volume form on symplectic volume form on any symplectic manifold. In this case, in this sense, Hamiltonian vector fields cannot be gradient vector fields. There cannot be, on compact manifold, you cannot find a vector field which is simultaneously Hamiltonian with respect to certain symplectic form and gradient with respect to some chosen Riemannian structure. It is just impossible. Think about this. However, we need compactness here. In non-compact case, this is possible. This is doable at least thinkable. Okay. So here we go. What is the consequence of this observation? It is the following, for instance. It is numerous, actually. One of the most important is the following. If you take, so put f and g, again up to the sign, I'm sorry if I'm making some mistake, minus x sub f applied to g. So when we have two functions, f and g, right, we can take Hamiltonian vector field induced by one of these functions and apply it, compute it at the second function. It will give us a third function on our manifold, and we shall denote this operation by brackets. So the properties of these brackets are quite interesting. So first of all, it is skew-symmetric. It is not evident in this case that this is the case. I think I wonder whether I should prove this or not. Actually, it is quite an exercise, but okay, let me do this exercise for you. So this is by definition minus x sub f of g, right? So what is this? So for any vector field, let me recall the definition of omega xf xg is equal to minus xg of f, right? It's by definition, right? So what we have here, it is vice versa. But it is actually, so since omega is skew-symmetric, it is minus xg xf. So it is minus plus xf of g. So if you look at this attentively, you obtain this formula precisely, right? Okay. So this is the first. Second, it is that this operation verifies the Leibniz rule with respect to both entries. Well, of course, it verifies Leibniz rule with respect to G, but since it's skew-symmetric, it verifies Leibniz rule with respect to F again, right? So Leibniz rule. And the last but not the least, but actually most important, it is that this operation verifies the Jacobi identity. I'm sorry. I need to erase this too. I cannot keep it. So in this case, the proof is pretty simple, in fact. But yeah, let me tell something. Actually, if we take F and apply it to GH, so what we do is that by definition, we take the minus x sub f and apply it to the function gh. Right? Now, if you look attentively at this definition, so there are different ways to do this, but I prefer the following one. This expression actually can be written as follows. F and g is again up to the sign equal to phi ij df dxi times tg gxj, right? Oh, you can also put it like this. If pi is the element in the wedge product, in the wedge square of tangent bundle, and we just take the differentials of f and g and apply and compute this bilinear form, bilinear element on these differentials. Now, if you look at this formula and you take Lie derivative of this formula with respect to any vector field, so if you take Lie derivative with respect to any vector field of this expression, you will see that Lie derivative, by the virtue of it being derivative, in fact, should be applied to all three elements entries in this formula, to pi, to f, and to g, right? So it is equal, more or less, Lie derivative of pi computed to df dg, then plus, it's two forms, so there is no sign, I think, right? Pi applied to Lie derivative actually commutes with differential, as you know, probably. D Lie derivative xf dg, and finally pi df d Lie derivative sub x of g. Right. Now pi is the inverse of omega, and since omega was preserved by Lie derivatives with respect to Hamiltonian vector field, this element also is preserved. So the first term in our formula vanishes, and what we have is just minus x f of g h minus, probably minus here, okay, it doesn't matter, and plus g minus x f h, right? And now, by definition, this is just the sum of f and g applied to h and x, f and h applied to g. And now it's precisely this formula up to the signs which we restore by permitting these elements due to the skew symmetricity. Actually, this form of writing the Jacobi identity is in some sense even more productive because it gives you some algebraic insight into the property of Jacobi identity. Jacobi identity actually says that the operation is a derivation with respect to itself. So that's what it says here. That's precisely what we obtained. And also I think it's a good exercise for anybody to prove that if you take two Hamiltonian vector fields, xf and xg, and take their commutator in the usual sense, and what you obtain will be the commutator, so the Hamiltonian vector field of the Poisson bracket of f and g. Yeah, sure, this notation is now justified. It is, this operation is called the Poisson bracket of f and g on symplectic manifold with respect to the given symplectic structure. Okay? Now we are in a purely abstract and coordinate-free setting, and we can define, at least introduce the problem which we are going to consider. It is the deformation quantization problem as it was first introduced by Moshe Flato in 1972, I believe. Or about that time. The question is, let me continue after I erase the backpart. The question is, suppose you have a symplectic manifold, so m omega, m to m omega, is a symplectic manifold. And you look now for the associative star product on the space of smooth functions on M, actually with respect to the formal variable h bar. So you can see the formal power series of h bar with coefficients in C infinity of M. And you look for the star product in the following sense. So first, or probably 0, as that the star product should be H linear, and again, this distributive law should be verified on both sides. That's very natural. Then, number 1, it should be associative. Number 2, so as I explained from linearity and distributivity, it follows that it is enough to determine the star product just on functions on M. And then this star product is given by a formal power series of this form, where bk of f and g is a bidifferential operator. When I say bidifferential operator, I just mean any expression which locally can be written as differential operator of certain degree in the first term and of the same of certain different degree of the second term, or rather sum of such terms, something like that. Is this clear? So bidifferential operator is expression of the form certain coefficient times certain partial derivation of some order applied to f, and certain partial derivation of some order, some different order probably applied to g. Okay? So this is the form. So the assumption that these bk are linear bidifferential operators is actually some assumption, because a generic map can be a very complicated degree, some complicated form. Yeah, if you just take some bilinear function of f and g, it can look, well, very complicated, very awkward, very very, I don't know, difficult to grasp. But bidifferential operators is something you can actually understand in a certain degree, up to a certain extent. So this is bidifferential operator. Yeah.
What does distributivity mean?
Distributivity means that when you take three functions f, g, and h, and you take a product of f times g plus h, you can express it as the sum of f times g plus f times h. Actually, you can do it in both ways. I mean, you can either take the sum on the left or on the right, and yeah, that's called distributivity.
Write down the formula for bidifferential operator.
Okay, sure. Just a moment. So locally, bidifferential operator has the form of some expression of form or something like. It should look like some sum of multi-indices I and j, and we have some coefficient a, I, j, probably k also somewhere here. Yeah. Of x. X is the coordinates. X are the coordinates. And then we have partial derivation d to the power I applied to f, d to the power j applied to g, d to the power I is actually di1 dx1 to the power I1 and so on, din d to the power in xn, and all these should be applied to f and so on. So this is kind of very natural construction in this field. Okay.
Some are finite.
Yeah?
Some are finite.
Yeah, the sum is finite, should be finite. Actually, these should be finite order differential operators on both degrees. Yeah, it should be finite order differential operator.
Is it possible to think about such operator with infinite?
It is possible, but it will make the whole story much more difficult. Almost, yeah, I don't know. It's actually one of the problems why people don't know what to do with infinite dimensional case. All standard formulas for for finite dimensional quantization cannot be applied to infinite dimensional case. You have to modify them somehow. As far as I know. Maybe something has appeared in recent years. Okay. This is the bidifferential operator. So this is the assumption. Okay, 1, 2, 3. And we go to number 4. It says that the first two bidifferential operators in this series should be specified to just the product of f and g, and then h bar divided by 2 times the Poisson bracket of f and g. Actually, this assumption can be justified independently. One can show that whenever you have kind of associative deformation of product, then up to certain identification, up to certain equivalence relation, the second term is always given by a Poisson bracket. Yeah, but we shall omit it for a while here, right? So then we have something of h. And when we have two more, sometimes, two more conditions which are sometimes removed because they are actually technical. So number 5 is that 1 is the unit, the identity function is the unit, and also that b n of fg is equal to the minus 1 times n to the power n bn of gf. So this Q symmetricity is sometimes assumed, sometimes not. So these two, I put them into brackets because they are in many cases removed, these two conditions. Oh, sorry. I forgot that I used 0 instead of 1 there. So yeah, sure, number 3. 3, 4, and 5. Yeah, sure. I wish all the questions were so simple. Okay. Okay, all remarks were so benign. Okay, let's put it this way then. Okay. So this is the thing we are looking for. This is the problem that was formulated by Marcel Flaton in 1972. And there are lots of examples which you can think of. So one example is the Moyle product. For example, is Moyle product. I already mentioned this. It is very natural. Yeah. Another example. Let me give this example before I proceed. Is the example of differential operators on a manifold, usual differential operators. Actually, one of the most standard and most important examples of symplectic structures and manifolds is the case when M is equal to the cotangent bundle of certain smooth manifold X. Smooth manifold. Then there is a canonical symplectic form, canonical symplectic structure, omega 2 on M, which can be written in the following way. So there, you can do it, for instance, in coordinates. If you have coordinates x1, xn, coordinates in x, and you have local coordinates in t star. So actually you have the basis dx1, dxn basis in t star of x, right? When you have a basis, you have coordinates, and these coordinates are usually denoted by psi. So psi1, psi-n are coordinates in the vertical direction of this cotangent bundle at any given point x, 0, right? And then the differential form omega is just the sum d, I think it should be like this, up to the sign again, dx, d psi I which dxi, sum over I from 1 to n. This is locally, this is local expression. Then you can check that when you change coordinates x in an arbitrary way, smooth way, in the base, and this expression actually remains invariant. So it means that in other coordinates, if you change coordinates accordingly, both in cotangent direction and in direction of the base, if these coordinates are changed simultaneously, then this expression is preserved. So in different coordinates you get the same expression. So this is a well-defined form, and it is clearly non-degenerate and clearly closed with respect to the drum differential, right? Yeah. Actually, there is an invariant way of introducing this form, something like, let me try to recall this invariant definition. So first we introduce a differential one form. So differential one form alpha, omega 1 and t star of x is such a form that its value at any tangent vector v is tangent to the cotangent bundle is equal to let me see, oh sorry, I forgot to say this should be tangent at certain element psi, right? Or probably I better say it should have two coordinates, x, comma psi, right? Any element, any element in tangent bundle T of cotangent bundle of x, yeah, is a vector applied at certain point of T star of x. So this point of T star of x has coordinates in direction of x, small x, and the coordinates in direction of the fiber, and this is psi. So this psi is a differential one form on x at point x small x, right? So this is psi is an element of T star of x at x capital, right? At x of x capital. Then there is a projection from T star of x to x, and then we apply a tangent functor to this. We obtain a projector from here to here, but that's denoted by this by pi. And finally we get the following formula. We take psi, this is a one form, we take pi of v. This is a vector tangent to x at point x small x, right? And we compute the value of psi at the vector pi of v. So this is an invariant way to define alpha of a differential one form alpha on T star of x, right? Locally, alpha has the form psi I dxi, sum over I, as far as I can understand, right? And then omega is just d alpha. Yeah, you can check this yourself, but for our purposes it's enough to know that this is the form. Okay, let's go on. So we have this differential one form, differential two form. It is closed, since it's actually it's not just closed, it's actually exact. As you see, it is well-defined, exact form, very nice. Then, yeah, since it's exact, it is closed, as they say, par excellence. Okay, and we go on. And then you have the Poisson bracket of functions on cotangent bundle and so on. And the question is, what is the star product there? Is it possible to define the star product? It turns out that in some sense it is possible to do. It is possible, it can be done. And let me briefly describe this construction. Actually, this can be made very, very exact, very rigorous, but I'm not going to go into detail. So the construction is as follows. We consider differential operators, linear differential operators on x. Any such differential operator d can be applied to a function f, and it has the form, as you as you can guess, A I, where I is a multi-index, model I is less or equal to K. K is the order of differential operator. Apply of X, and then you take partial D sub I of F. Right? This is the differential operator. Differential operators, well, they are natural operators. You can take the sum, take the multiply them by functions, multiply them by numbers, and so on. So they are linear. They make up a linear space. But you can also take compositions of differential operators. So when you have two differential operators, D and P, P and Q probably better, you can take the composition in this direction, in this order, and also in opposite order, and they need not commute, of course, since this need not be constant, right? So this is non-zero. So the algebra of differential operators is a non-commutative associative algebra associated with every smooth manifold. There can be some technical difficulties with changing coordinates from one local system to another local coordinate system. So this actually takes some time to make up all details. But at least locally, at least on Euclidean spaces, there is no problem introducing these differential operators, right? Nice. Then we have done this last time when I spoke in the end of my last lecture about the relation between Weyl algebra and Moyle product. So here we have differential operators. They are well defined. Then for every differential operator you can associate its symbol. Okay, so symbol of differential operator. A complete symbol of differential operator is locally well defined. It is a function of the following form. It is sum over the same multi-indices I up to degree k, a sub I of x. And now instead of taking d, we take psi to the power I. So psi are local coordinates in vertical direction in the cotangent bundle. So these are functions on the cotangent bundle of x. And now you can regard these two formulas as actually kind of quantization of the space of functions on cotangent bundle. So when you go from functions to differential operators, this can be done somehow. You actually quantize the functions, and with respect to precisely that symplectic structure which I mentioned before. In order to restore this symplectic structure from this construction, you can do the following trick. You can actually consider the filtration of differential operators by their orders, by their degrees, right? So then you have two differential operators, one of order P, the other one of order Q. The difference, the commutator is differential operator of degree P plus Q minus 1. So the order of this commutator is P plus Q minus 1. Yes, it is, actually less or equal to this. Yeah, actually it's better to say less or equal to that. Because it can be sometimes it can just commute. So in that case, it is not quite clear what kind of order you can introduce, but yeah, minus infinity, that's true. Yeah, it's a good question. So in any case, we have this, and then if you actually quotient out all differential operators of degree of order strictly less than p plus q minus 1. So if you take the commutator of p and q and quotient out all the differential operators of degree strictly less than p plus q minus 1, you obtain precisely the Poisson bracket, but not of the symbols of these operators, but rather of principal symbols of these operators. So sigma p and sigma q. So principal symbol is just when the only difference between the symbol, the complete symbol, and principal symbol is that I use only the sum over all i's whose model is exactly equal to k. But the sum is the same. So yeah, just to cut the long story short. Sorry? Yeah, I just didn't want to go into this formula, but okay. But it's actually the same, so this is just actually the same. Yeah. Well, do not say that this is the way you introduce this product in functions, but it is, well, roughly speaking, it is inspired by this formula. The actual construction is a little bit more delicate, the actual construction, but not too delicate. Okay.
Excuse me.
All right.
So large P and large Q are differential operators.
Yeah.
And what does P, large P sub small p mean?
Sorry?
P small is just a number.
Yeah, it's P small p and q, p and small p and q are just the order, of differential operators. Yeah. So the order of p, the order of p capital is, the order of capital P is small p, the order of capital Q is small q. So these are just orders of differential operators. Okay. So this example is well known, and one of the questions, one of the most, in my opinion, remarkable constructions in this field is the construction of star product associated with any symplectic manifold, not just with cotangent bundle, but with any symplectic manifold. So I'm going to start explaining this construction right now, but before I do this, I just want to mention that this is not the most general way to formulate the deformation quantization problem. I didn't speak about the Poisson structure, genuine Poisson structure, which are not non-symplectic, but genuine Poisson structure. One can actually speak about Poisson structures and so on. The question of finding star product associated with genuine Poisson structure has also been answered. It is due to its famous result due to Maxim Kontsevich. It's even more interesting that, in some sense, it's less geometric, but it has very deep relations with various branches of mathematics, of modern mathematics. Yeah. So, but in my opinion, Fedosov's construction is really worth studying independently of Kontsevich's construction. It is quite geometric and nice. So, Fedosov construction. So, by the way, how much time do I still have? What time is it now? 10 minutes.
Maybe more.
Okay, so then I just
15 or 20.
then I just give some introduction into this. Okay, I give a kind of survey of the main ideas which is inside, and next time I probably explain the details of this construction. So the main ideas are pretty natural and remarkably simple, in my opinion. Suppose I have a linear space of any nature, S. then to introduce star product or any associative product in this space, one can do the following thing. Take any linear isomorphism that's denoted by sigma from S to any associative algebra A. So you have this linear isomorphism. And then, if you want now to take the product of two elements, V and W, in S, you just do the following thing. You take sigma, apply it to V, take sigma, apply it to W. Now you have two elements in the algebra. And in algebra, you know that there is a product. You take this product in algebra, and then you take the inverse isomorphism, sigma. Since sigma is only linear, yeah, it's just linear map, linear isomorphism, you cannot remove sigma from here, What you obtain will be a genuine star product, V star W. It will automatically be associative. Yeah, but just by definition it will be associative. There is no problem. And since sigma is also linear, it will also be distributive. So all the conditions, all the natural conditions on the product which you want to introduce are satisfied. Constructions like this were known before. For instance, the famous Poincare-Hopf-Witt theorem gives you a way to quantize in this, by this trick, quantize polynomial functions on a co-adjoint representation of a Lie algebra. Yeah, functions on co-adjoint representation of a Lie algebra. However, Fedosov's idea was to apply this sort of construction to very large space, C infinity of manifold M, or in more general, C infinity of M and with coefficients in H bar, actually, to this space. So Fedosov's idea was to take S equal to this, right? The problem is that the algebra on the right will be very large, and actually I'm not sure if any such algebra, explicitly known algebra, exists. So that was the first idea. So the next idea was to modify the right-hand side a little bit, to make it a bit larger, and then choose a proper subalgebra inside. Actually, what Fedosov did, he said, let us take a large algebra, W on the right. And then instead of taking linear isomorphism, which is, well, impracticable, it's too large. Everything is too large and we have barely any control over what happens. We look for some subalgebra. Let's call it. Yeah, sigma minus first, right. Yeah, I forgot about this. Sorry. I said it, but I actually didn't write this. So we return it back. So S, okay, sure. So instead of taking algebra here, we look for certain subalgebra A inside this large algebra W. Unlike this large algebra W, which we have some control of, this subalgebra A should be defined a little bit in an abstract way. Yeah? So we don't know how this subalgebra A actually looks. We just know that there exists a linear isomorphism between S and A, and that A is a subalgebra in W. So now we're looking for a nice way to introduce subalgebras inside large algebras. So one of the most interesting ways to do this is by considering a differentiation of algebra. Let me recall you the definition. if you have an associative algebra of any nature, of any sort, W, a differentiation D of W is a map from W to itself such that D of AB is equal to what is given by Leibniz rule, dA times B plus A times dB. As you see, I'm not using commutativity. So dA times B is not equal to B dA. And the same here, right? So this is the generalized Leibniz rule. Now, if you have a differentiation D, then the space W sub D, which is just the kernel of this differentiation, the space of, so to say, flat sections of W with respect to this differentiation D, is naturally a subalgebra, just because if you look at two elements, A and B, which are flat, and their product, according to the Leibniz rule, will also be flat. So, philosophy now looks for some large algebra W equipped with some differentiation D such that the space of flat sections with respect to this differentiation will be linearly isomorphic to the space of smooth functions on M. And that's the main idea. And now all the ingredients are readily obtained from local data, from the local data. So first of all, it is quite easy to guess what kind of algebra W we shall need. Just like before, we are going to deal with some differential operators. But this time, these differential operators will be algebraic. Namely, last time I spoke, I introduced Weil algebra. W, well, W now stands for Weil. Yeah, Hermann Weil. I think, not André Weil, right? Hermann Weil. W of R to N, let me recall you, is the space of non-commutative polynomials in two n variables, x1, xn, probably x1, xn, like these d1, dn. So these are non-commutative variables, quotient by the only one relation, that the commutator of di with xj is equal to delta ij. Right? Now, this is very natural way to write down these relations, however, not the most general one. Actually, last time I spoke about Moyle product, I already modified this relation so that it will embrace the case of non-canonically written symplectic tensor, symplectic form. So actually, if we have a symplectic form omega, so that its inverse pi is our bivector, right? Then we can write down the same relation here in a more abstract and coordinate-free way. Not coordinate-free, but not totally coordinate-free, but let us say coordinate-independent way. So we have 2n coordinates, y1 through y to n. These coordinates are now totally so how do you call this? They have I forgot the word. In Russian, it's равноправные. How do you say it in English? No, not democratic. So what is? Can you look it up in a dictionary for me? I would be very grateful. So yeah, not independent. They are all on the same grounds, so to say. None of them has any privilege. None of them is certified to be coordinate in a space or coordinate in cotangent space direction. So they're all equal in their right, but the relation is written in the following way. You take yi and commute with yj, so what you get is pi ij, just this. Sometimes just in physical literature, it is important to keep trace of the imaginary unit. So I probably will introduce it here, -1, square root of -1. This is imaginary unit. And also I'll introduce the Planck constant, this formal variable h bar here, right? So this will be our Weil algebra. It is precisely the same algebra as here with only two corrections. We have this coefficient square root of -1, and this means that we need to pass to complex coefficients here. Of course, complex coefficients are by no means important here, but they're just kind of a duty we pay to the physical nature of the physical origins of this whole story. And h bar is our formal parameter. It is important to keep trace of our commutators. So this is the Weil algebra in vector space R to n. Now we have a 2n-dimensional symplectic manifold M.
Actually, it's not important what is the field there. You can put there even Q.
Well, then square root of -1. What shall we do with?
Add root of minus.
Yeah, but yeah, if you have some algebraic mind, if you algebraically minded, you can work with arbitrary field here, right? Here, right?
But because this object doesn't need anything.
Yeah, here in a few moments, I'll need this. Because I'm going to introduce a family of Weil algebras parameterized by points in a symplectic manifold. And it is very natural, actually. That was the purpose of introducing this algebra. So now we have a symplectic manifold M, and we consider its tangent bundle. At any point x0 here, a tangent space, tangent plane of M at point x0 is just R to n. Right? Then if we have local coordinates in M, x1, x to n, local coordinates, you get local coordinates y1, y to n in R to n, right? Probably better to speak about cotangent bundle, actually. You see, I'm keeping trace. So these are upper coordinates, yeah. So if I want to keep upper coefficients, they should probably be with here, right? Functions on cotangent space are elements on tangents in tangent space. So yeah, it's correct to do this, I think, right? Okay. Anyway, okay, so we have this. Now, if we take this bivector pi, then in these coordinates, x1, x to n, you can write it down as an element, as a matrix valued function on M locally. And that means that at any point x0, you have this sort of function, this sort of algebra. W of t upper star of x0 of m with respect to this pi. Now you can also use c here and h here to underline the fact that you are using complex coefficients, and you use formal variable h bar here.
Do you still assume that pi?
Sorry?
Do you still assume that pi is constant?
No. It's constant with respect to y. When you change y's, you don't change pi. But when you change base coordinates in the base, you change pi. That's the problem. So for any fixed coordinate system in M, you have a matrix valued function. At every fiber of our cotangent space, the cotangent bundle, you have a constant matrix. So in this fiber, you have a very well-defined Weil algebra. Now, if you change coordinates, it is an easy exercise to check that changing coordinates does not change this relation, because the left-hand side and the right-hand side change simultaneously, and you get the same relation in u coordinates, in prime coordinates, for instance. So you get a well-defined family of Weil algebras over the manifold, parameterized by points in this manifold. In abstract terms, you get a fiber bundle of Weil algebras over the manifold. For those of you who are familiar with the terminology of fiber bundles, principal bundles, their associated vector bundles, what I have just done is the following thing. I took the principal bundle associated with my manifold, the principal frame bundle associated with my manifold. I restricted the structure group to symplectic group. I can do this because I have symplectic structure. Yeah, so I chose the symplectic frame bundle on my manifold. Then I have symplectic group action on Weil algebra. Symplectic group acts on Weil algebra by preserving the algebraic structure, preserving the product. And then I took the cross product of this principal bundle over the symplectic group action with the standard Weil algebra. Of course, with complex coefficients and with h bar. Unfortunately, I cannot use rational coefficients here, just because when I change coordinates, I lose control over the rationality or irrationality of the coefficients I obtain. Yeah? Yeah. But if you work, for instance, some algebraic category and your manifold is algebraic, and you have some, by definition, you have some, well, restriction on the coefficients you obtain, then of course you can do this trick over any ground field.
But there are interesting problems exactly over Q.
Mm-hmm.
In particular, this Chikovan conjecture, Dix-Meck conjecture is
Yeah,
very
sure.
relevant.
Yeah. Mm-hmm.
It's even maybe easy to fault for Q.
Yeah, maybe. I'm not sure. Okay, so now we have this. And sections of this, smooth sections of this fiber bundle, or you can say when you have a family of Weil algebras parameterized by the points in M, then you can take sections of this family. That is, you take kind of functions in M with values in algebras of this family, right? And these functions, these sections of our fiber bundle, will be the algebra W which Fedosov introduced. Well, you need some technical manipulations with this to make sure that everything converges as it should, but I'll speak about these technical manipulations next time when we speak about technical issues. So the sections of this fiber bundle, let me call it W, probably precisely what I have already written, WC sub H T star of M, comma, pi. So the sections of this WC sub H T star M, comma, pi will be my algebra W. Now, when you have a fiber bundle, you can consider connections in this fiber bundle. Connections of this of any fiber bundle, especially of vector bundle, are rules which allow you to differentiate sections of your fiber bundle with respect to vector fields in the base. Right? Then what Fedosov does, he introduces a very special class of connections. They are called nowadays Fedosov's connections, but Fedosov himself called them abelian connections. On W. These connections, they're more than just one such connection. Actually, these connections are classified in a very nice way by elements of the second Duranko homology of the base space M. So for any such connection, you can consider now the space of flat sections with respect to this connection. And this space can be identified in a very nice way, in a linear way, with the space of smooth functions on manifold M, well, decorated by the formal variable h bar. And that's more or less how the construction is done. So now there are lots of technicalities over there. In order to, first of all, I need to modify the definition of Weil algebras in order to allow infinite sums over there. And that's not very hard, but it needs some technical, well, I will need to solve some technical issues. Then the definition of Fedosov's connection is very natural, but the existence of Fedosov's connection is far from being clear from the definition. So you need to work a little bit, well, not too much, but more than just simple observation to prove the existence of abelian connections. Then for any abelian connection, you of course have this algebra, but to prove that this algebra is linearly isomorphic to the space of functions decorated by formal parameter h bar, is also some work. And eventually, you need to prove that the product verifies all the conditions except for technical ones, which I mentioned, of star product. And also, I'll probably speak next time about the classification of all Fedosov's products. And that will probably only cover the case of real number valued functions and real symplectic forms. Because if you speak about, for instance, complex analytic symplectic forms and complex analytic star product, it is a separate issue, and I really want that some of our young people make a talk about this. That is, in that case, there is a very nice paper due to Nest and Sigan. This paper is 20-something years old, 22 probably years old. And one can think that all the problems raised by that paper has already been resolved, but that's not true. The problem introduces series of characteristic classes, which are nowadays called Nest-Ziegen classes, and the nature of these classes and their properties is the subject of much debate. At least they are probably not much debate, that's to say too much, but specialists know that they are mysterious in many things, in many respects. Okay, that's all. Now I just wait for the questions, if there are any.
Вопросов вроде нет.
Yeah. Задавайте.
Можете по-русски задавать, они все равно не слышат.
Я немножко прослушал, а вот как решается задача для касательного расслоения?
А в касательном расслоении я, значит, сказал так. Я показал вам, что есть некоторая уже готовая некоммутативная алгебра, называется алгебра дифференциальных операторов. В этой алгебре, эта алгебра тесно связана с алгеброй функций при помощи символов, точнее при помощи главных символов прежде всего. То есть я могу с каждым оператором связать некоторую функцию на кокасательном пространстве, называется главный символ, скажем, оператора. Тогда я могу, тогда для этих, значит, функций я могу ввести уже Пуассонову структуру, Пуассонову скобку Пуассона, исходя из чисто вот операторного умножения. Я возьму два оператора в одном порядке, возьму их в другом порядке, вычту эти композиции друг из друга, и то, что получу, возьму старший символ. И тогда то, что получится, будет давать скобку Пуассона на символах. И вот эта скобка Пуассона будет в точности той скобкой, которая на функциях на кокасательном пространстве связана с той Пуассоновой структурой, симметрической структурой, которую я там вводил. Вот. Значит,
это какое-то утверждение как бы...
В обратную сторону, вы хотели сказать. Да, я двигаюсь в обратную сторону. Ну, по существу я вместо того, чтобы строить звездочка произведения на функциях, я получил функции вместе с Пуассоновой структурой, исходя из некоторой некоммутативной алгебры. Я в обратную сторону сделал. Вот. Это нечестно, конечно, вы правы совершенно. По-настоящему я должен был бы взять функции на кокасательном пространстве, спросить, что такое теперь звездочка умножения на них, проверить, что все эти операторы b, каты могут быть построены, и получить звездочку умножения. Но значит, это некоторая теория, которая просто займет еще одну лекцию.
Нет, ну все-таки
Техника
техника.
то, что я сказал, это не техника, это объяснение того, откуда берутся дифференциальные операторы в науке про звездочку умножения. Что мы можем... Это просто наблюдение о том, что если возьму эти операторы, то они, с одной стороны, с помощью символов могут быть отождествлены с функциями, и тем самым можно сказать, что эти операторы и умножение на них, вот эта вот композиция, это и есть звездочка умножения на функциях. И даже при этом можно проверить, что по первому порядку малости эта звездочка умножения совпадает со скобкой Пуассона, которую я вводил. Но это, конечно, не объяснение того, как именно звездочка умножения вводится на таких функциях. Там требуется немножечко больше работы. Но это займет, повторяю, еще одну лекцию. Вот. А результат будет в некотором смысле геометрически тем же самым. Нет, это хороший вопрос, это правильный вопрос. По-настоящему связь между дифференциальными операторами настоящими и звездочкой умножения — это такая связь отчасти мистическая. Сам Федосов, кстати, этим много занимался. И что он прежде всего строил свою звездочку умножения для того, чтобы как раз изучать дифференциальные операторы. Потому что звездочка умножения — это как бы упрощенное умножение на операторах. В операторах есть большая аналитическая наука, которая сама по себе непростая, и она при этом затрудняет использование их алгебраических свойств. Вот если мы как-то так пытаемся их сделать. Более-менее алгебраическая наука хорошо действует, хорошо работает на плоских пространствах. Да? Вот алгебра Вейля — это по существу алгебра дифференциальных операторов на евклидовом пространстве. А если пространство у нас кривое, то вот такая конструкция алгебры Вейля уже не работает. А с дифференциальными операторами хочется работать. Вот. И Федосов рассматривал свою звездочку умножения как такой вот алгебраический подход к дифференциальным операторам, как алгебраическую замену дифференциальным операторам. И он пытался даже какие-то аналитические вопросы по дифференциальные операторы решить с помощью этой вот алгебры. Ну, как я понимаю, то, что у него получилось, не совсем решает аналитические задачи, но само по себе крайне интересно. Вот так.
Джунку спрашивает, что там сегодня, что там обсуждается.
Oh, sorry for speaking Russian, because the question was asked in Russian. I was explaining the construction which relates differential operators with Fedosov quantization. Actually, you can regard Fedosov's quantization as an algebraic approach to the study of differential operators. And that was the original motivation of Fedosov. And when I spoke about differential operators and quantization of cotangent bundle, I actually tried to reverse this idea. I tried to introduce a star product from the product of differential operators. That was cheating, I must confess. That was not honest. There was some cheating there. Yeah, so you can regard that part of my talk as kind of motivational talk rather than some strict statement, some rigorous statement. Okay. Any other question or comment?
I hope you explained. So I wrote him what was the question, and you explained it again.
Yeah, okay.
In English, so I hope now everything
Okay.
is clear. Well, but okay. I wait for a minute, but I think.
Okay, then I just stop this conference, and we shall reconvene again in a week. Thank you everybody for being here, and see you next time in a week. Bye bye. Окей. А там появился мой этот ван?
Не был, но может он смотрел YouTube.
Может быть. Значит, я ему точно послал, все, мы посмотрим.
Ну, сегодня тоже там количество слушателей менялось там от 12 до 1, то есть в сумме где-то у нас было больше 10 все время.
Ничего себе. Ничего
Кто-то
себе.
слушал через YouTube, кто-то через Zoom.
Интересно как.
Часть офлайн.
Okay.